Hi everybody. In this video I want to discuss the dynamics of simple harmonic motion for a simple mass spring system. All right, so here's a sketch of the system that I'm talking about. So I've got an immobile wall, I've got a frictionless surface, notice no friction, I've got a spring, and this spring is a spring that's capable both of compression and expansion or extension. So I've attached a mass, a block here of mass m, and this would be the equilibrium position. So this, when the mass is attached to the spring right here, the spring is neither stretched nor compressed. So I'll track the middle of the mass, and I'm going to call this location of the middle of the mass at this equilibrium position. I'll call that x equals 0. All right, now we could set this thing in motion. We could pull this to the right by an amount a, let it go, and this thing will oscillate back and forth in simple harmonic motion. Since there's no friction, and we'll assume that we've got all really nice connections here, the system will not bleed. This idealized system will not bleed energy to the environment, so the mechanical energy of the system will remain constant, and so basically this thing will just keep going back and forth between x equals plus a and x equals minus a forever. So we want to basically apply Newton's second law to this system to try and figure out an expression for the position as a function of time for the mass under these conditions. All right, so I'm going to take to the right as the positive x direction. That's implied in the way I've written this. So here's x equals 0. Here are positive locations of x. Here are negative locations of x. So the positive x direction is this way. All right, so this is our system. So now let's apply Newton's second law to analyze this system. Well, the first thing we need to do is to consider all the forces acting on this mass. So that's what we're going to look at. We're going to be tracking this mass. We're going to assume that the spring itself has negligible mass so that you don't have concerns worried about the acceleration of the spring itself. The spring itself is approximately massless, we'll assume, or it's so much less mass than the mass of the block that we can ignore the effects of the mass of the spring in this analysis. That's an idealized model. All right, so let's draw a free body diagram of the forces acting on this mass. Now, there's lots of different locations in here. I want to just sort of represent them all in one shot. Let's imagine when the mass is located right here and draw a free body diagram of the forces acting on that mass. So boom, imagine this over here. Boom. So this is the mass. I've drawn that. There'll be the downward force of gravity of magnitude mg, where g is 9.8 meters per second. M is the mass of the block. We've got the normal force that the surface, the frictionless surface, exerts upward on the block. We don't have a frictional force because this is a frictionless surface. We've assumed that to just idealize our simple harmonic motion. We do, however, have a force that the spring exerts on the mass. And I've put a little asterisk next to it because it actually depends on where the mass is. If the mass is over here to the right of equilibrium, the spring force will point toward the left. If the mass is over here to the left of equilibrium, the spring force will point toward the right. So I've represented the situation with our force arrows for when the mass is right here. In that case, the spring force would point toward the left because this is representing the forces when it's at this location to the right of x equals 0. However, it turns out, I mean, if we're careful, this free body diagram or the things we come up with this can represent the situation all throughout its motion. And so here's how we're going to do that. These represent magnitudes, but this represents a force component. So that's why I've got a little asterisk next to it. Normally on my free body diagrams, I like to label the force arrows with magnitudes of forces and then put in plus or minus signs by hand according to my coordinate system. Well, in this case, I'm going to treat this one a little different. This is representing a force component, which could be positive or negative in the context of our x component of our coordinate system. Minus kx, that already builds in that plus or minus. So when x is positive, the force component would be negative. What that would mean is in this location, if the position is located to the right of equilibrium in this picture, that's positive x. My force component would be in the direction of negative x. So that's pretty clear. And I better just label this as the positive x direction just to make sure we've got that. All right. On the other hand, if the mass were located to the left of equilibrium, and we are drawing a picture, we wouldn't have an arrow over here, we'd have an arrow over here, but this equation would still represent things correctly, because if the mass was to the left of equilibrium, we'd put a negative value in for x, minus a minus would give me a positive value for the force, x component of the spring force, which would be this way. Great. All right, so now let's utilize this with Newton's second law to determine the equation of motion for the mass on the spring. All right, so first thing we note, in the vertical direction, there's not going to be any acceleration. I mean, if this were bigger than this, it would fly off it would start to accelerate off the surface. But there's no reason this would be bigger than this. If this ever got bigger than this and it left the surface, you wouldn't have a normal force. So that doesn't make any sense. Likewise, it's not going to sink into the surface. So there's no acceleration in this direction. Therefore, this thing must balance that thing. Great. So we don't have to worry about the vertical direction. All the action for our analysis is going to be involved in the horizontal direction. All right, so I'm going to look at the Newton's second law in the horizontal direction. Sum of the forces acting on the mass in the x direction will equal the mass of the mass times its acceleration component in the x direction. That's Newton's second law in component form. All right, so now we go look at our free body diagram. What forces do we have acting on this system in the x direction? Just this one. So this is already in the form of components. So in the place of the sum of all the forces in the x direction, we only have this. So we have minus kx equals ma sub x. Let's rearrange this. I'm going to solve for a sub x. A sub x will equal minus k over m x. All right. Now let's just do a little bit more work here. The acceleration in the x direction, that's the derivative of the x component of the velocity with respect to time. But the x component of the velocity with respect to time is the derivative of the x component of the x coordinate, with respect to time. So the acceleration in the x direction is the second derivative of x with respect to time. All right, and that equals minus k over m x. So this is a differential equation. The way we solve these differential equations often comes down to guessing and checking a solution. All right, so you'll go over equations like this in much more detail in your differential equations course. Some of you may have already taken such a course. Here, so I won't go over all the details. I'll just go over some highlights. All right, so often it's useful to make a substitution. Let's make a substitution. I'm going to take this k over m, and I'm going to write it as something else. I'm going to call minus, so k over m, I'm going to call omega squared. And that's just a substitution. So this whole k over m, I'm just making this substitution that k over m, just define that to be omega squared. All right, so now this is just math. We have the second derivative of x with respect to time equals the negative of some constant squared times x. So we've got the derivative of something, second derivative of something equals the negative of a constant squared times that something. All right, this is a very common differential equation. So we need to look for functions that when you take two derivatives of them with respect to time, give you back that function. So I have a function, take two derivatives of it with respect to time. I need to get the function back and a negative sign and some constant squared. So it turns out, and you can check this for yourself, that some specific solutions, I'll call them specific solutions, we have x equals, and this isn't the general solution. I'm just going to sort of put them in a little bracket here. It turns out that cosine of omega t would be a solution. sine of omega t would be a solution. And I can fit it right here. E to the plus or minus I omega t would also be a solution. I've really written two solutions right there. OK, so now I'm going to go over like 2 or 3 classes worth of differential equations in a couple of minutes. This is a second order ordinary differential equation. There's a theorem in differential equations that you'll probably prove if and when you take that course that comes out something like this. If you've got a second order ordinary differential equations, you can form the general solution by putting together 2 linearly independent specific solutions. So linear dependence is a whole other topic which you'll explore in your differential equations course. So there's lots of solutions here. There's basically 4 specific ones we've looked at: cosine, sine, e to the plus I omega t, e to the minus I omega t. They're not all linearly independent. Some of them are linearly independent. So it turns out we can nicely write the solution this way. So now we'll go to general solutions. General solutions. And all of these forms will be general solutions. So x equals, let's write it this way, c1 cosine omega t plus c2 sine omega t. Another general solution, another way of writing it, which turns out to be mathematically identical, mathematically equivalent, is, let's call it d1 e to the I omega t plus d2 e to the minus I omega t. And I may or may not have mentioned it earlier. This I running around here is the imaginary number, the square root of -1. These can be shown to be equivalent using trigonometry and various identities, namely the Euler identity, which relates the complex exponentials to cosine and sine functions. So in these solutions, omega is this omega here. There's another way to write this. X equals a sine omega t plus theta, where a and theta are arbitrary constants. So we're still satisfying that we need 2 arbitrary constants in our solution. It turns out that a cosine and a sine can be formed together to make just a sine function with relationships between theta, c1, c2, and a and c1 and c2, and so forth. Great. Now, you know that sines are just shifted cosines. So here's another way to write the solution. A cosine omega t plus phi. I'll use a different symbol for the phase constant. All right, in all these cases, omega is equal to the square root of k over m, where k, remember, is the spring constant in the Hooke's law force for the force that springs exert. M is the mass of the block. So we have a result, and this result is interesting. This parameter, omega, turns out to be something we'd call the angular frequency. And so we have a relationship between the angular frequency and the spring constant of the spring and the mass of the block. And so this is this basically makes a testable prediction. I'll talk a little bit in another video why this omega in an equation that involves a sine or a cosine like this, an omega before a t, why that represents angular frequency. All right, so the last thing we should do is actually check that these are all really solutions to this differential equation. I'm not going to check them all. Really, it suffices to know that if this is a solution and this is a solution and these are solutions, if you've really checked those, then linear combinations of solutions to differential equations should also be solutions. All these are legitimate. The forms we will use most of the time We use these because these are most useful for visualizing what's going on with simple harmonic motion. Very briefly, for example, the maximum value that a sine or cosine function can take on is 1. So in either of these two equations, the symbol A is representing the amplitude. So maximum value of cosine of stuff is 1, so x can be equal to positive a. That's its maximum value. That's the definition of amplitude. On the other hand, the biggest negative value that a cosine function can take on is -1. So x goes between minus a and positive a. And you can get that from either of these two equations. All right, so what we should do next is verify that one of these, at least, is go through the exercise of checking that when we take two derivatives of this function, it satisfies this differential equation that we obtained from using our Newton's second law analysis. So let's do that now. So let's check this form of the general solution. The derivative of x with respect to t, dx dt. Well, I've got this leading constant, so that flies through. Now I've got the derivative of the cosine of a function of t. Derivative of a cosine of a function of t with respect to t will be minus sine of that function of t. Now, part of that derivative is finishing with the chain rule. So I have to also take the derivative of this function of t. This function of t, omega t plus phi. Phi is a constant. Omega is a constant. The derivative of this, omega t plus phi, with respect to t, will just be omega. All right, so that's dx dt. Now, I need the second derivative of x with respect to t. So I need to take one more derivative with respect to time, d2x dt sub 2. All right, and so let me take the derivative of all of this with respect to time. Now, let me pull out my constants. I've got a minus sign. That's a constant, -1. I've got an a. That's a constant. My omega is a constant. So now I'm taking the derivative of the sine of this function of t with respect to t. The derivative of sine of a function of t with respect to t is just cosine of a function of t. So I've got cosine omega t plus phi. Now again, I need to finish out the chain rule. So I still have to take the derivative of this function of t with respect to t. Derivative of omega t plus phi with respect to t will be omega, because phi is a constant and omega is a constant. So now I put it all together. Second derivative of x with respect to t is equal to minus omega and omega, so minus omega squared. And I have a cosine omega t plus phi, but a cosine omega t plus phi was just x. So in fact, this does check out. All right, so that's about all I wanted to do with this Newton's second law analysis of simple harmonic motion. Big takeaways. One, we're just using Newton's second law and noting that the single force that's important horizontally is just the spring force, the force that the spring exerts on the mass. So we plug that into the left-hand side of our Newton's second law for the sum of the forces in the x direction. We just work this out, rearrange it, and we get an expression for the acceleration, which we can just rewrite as this differential equation. This part here is just a substitution to organize the math, but part of what has come out here is this parameter omega, which turns out to be the angular frequency, as we'll talk about in another video, is related to physical properties of the spring, the mass spring system. It depends on the spring constant, K. It depends on the mass, M. The greater the spring constant, the greater the angular frequency. The greater the mass, the less the angular frequency. All right, and the last thing is that to solve this, we use a guess and check method where we Basically did a couple days worth of a differential equations class in 5 minutes. We have many different equivalent forms of the general solution. These are the most useful forms. And we just performed a guess and check operation to verify that this is indeed a legitimate solution to this equation. All right, thank you.